So our last speaker of this event is Professor Yamamoto from Keio University. So Professor Yamamoto received his PhD degree in information physics and computing from the University of Tokyo in 2004. From 2003 to 2007, he was a research fellow at the Japan Society for the Promotion of Science. He was a postdoctoral fellow at the California Institute of Technology through 2004 to 2007, and at the Australian National University from 2007 to 2008. He's currently professor at the Department of Applied Physics and Information Physics in Keio University and the chair of Keio Quantum Computing Center. And his research interests include quantum computation and quantum control. Yamamoto Sensei, thank you.
Thanks for introduction. Naoki Yamamoto from Keio University, and I was thinking what is a good topic in this workshop, and I decided to choose the machine learning application yesterday. So I chose these four topics. One is overfitting and legalization, which is also occurred in the classical machine learning, data encoding and application to finance. And GAN is also a good hot topic in the classical machine learning. And lastly, I'd like to show you the fundamentals in quantum machine learning and an extension to the quantum case. So the first one is I borrowed this. So this one. So this paper explains the concept very well, and the concept is clear. Here's a quantum circuit, and X is an input data is encoded into the quantum state, and that is processed, and the subsequent quantum unitary, which contains the parameters. And we look at the function by measuring the first qubit and calculate the mean. So this is an output function of the entire network. So this is sometimes called the quantum neural network. So the idea is similar to the classical case. So we wanted to minimize this cost function by changing the parameters. So using the gradient method as usual, so we can train the whole entire circuit to determine the parameters. So this is a training set, and this is the cost function depending on the training set. And actually, this is a simulation from this paper. This blue is the training data, and the initial guess is illustrated in the green line, and finally they got the approximator, which were fitted into the hidden target function. Yeah, so this is the concept of quantum machine learning. But we have to be careful about how to construct a function, or in other words, how to design a quantum circuit, because the expressibility is a key in the final performance. So in this paper, they propose an idea of using the repeated use of the anti-encoding process. And actually in this paper, they just use the encoding process once and later use the parameterized quantum circuit. But in this proposal, the encoding process is repeatedly used like this. So then looking at the Fourier transform of the output function, we can see actually by repeating the encoding process, the expressibility can be enhanced. So this is an example. If you use an encoding process just once, then for a single qubit case, this is a sinusoidal single frequency sinusoidal function appears. So it is less expressive. The expressibility is poor. But if you use a encoding process 3 times, then you can see this red line actually has a better expressibility. And if you use encoding process 5 times, then finally the output function can approximate the hidden target function very well. So this repetition of the data encoding circuit is quite important to enhance the expressibility of the quantum circuit. And of course, but as is well known in the classical case, if you increase expressivity too much, then your approximator is fitted to the training data too much, which is called the overfitting. So we propose an idea to avoid such an overfitting issue using the similar idea often used in the classical machine learning, which is called the dropout. So I lead this one. So too much expressibility leads to overfitting, as usual in the classical case. So the dropout is used. So the idea is to randomly remove the edges of the neural network to reduce the expressibility. And we applied this idea to the quantum case, which corresponds to randomly removing the CNOT gate or entangling gate. That's a quite simple idea, I think. So this is an idea. So part of the quantum circuit, and we randomly drop out removes the entangling gate like this. Then actually this resulting circuit has less expressibility, but can avoid the overfitting issue. And actually, from this figure, without such an dropout, then this resulting function illustrated in the orange line is fitted to the training data too much. So this is overfitting. But introducing the dropout, you can avoid such overfitting. Yeah. So the concept of this showcase is actually we can use the idea of classical machine learning to enhance the performance in quantum machine learning as well. Actually, there's no theoretical proof for avoiding overfitting, but and this simulation result suggests us to use this idea later on in for practical applications. And the second part is application to finance and again for classifiers. So this paper, just one slide. So this paper proposed the efficient encoding scheme of the classical data to the quantum state. And actually, in machine learning application, it is crucial how to encode the classical data into the quantum state, because in general, it requires exponentially large number of operations, which is of course inefficient. So we have to reduce the number of operations. In this paper, we take the variational approach to do this task. Okay, so use variational quantum algorithm to approximate an ideal encoder. So this is the ideal target. So DJ is represents the classical data. So it has the exponentially huge number of vectors. And of course, we cannot realize this one in usual scheme. So we want to approximate this guy by changing the parameters of the parameterized quantum circuit. And it's of course, in this case, the problem is what is a good measure and the cost function, and how to optimize and how to minimize such a cost function. And in this work, and we take the minimum mean discrepancy cost to measure distance between two distributions. And actually, this DJ can take a negative sign. So this itself doesn't correspond to the probability distribution, but we transform this information to some kind of the probability distribution, and we used the minimum mean discrepancy measure to as a cost. And the usual optimizer minimizing this cost function works, and and this is the application. And I think this is an interesting application, and actually this work is a collaboration with Keio and banks, and they have interesting problems. I think this is a good example of the collaboration between the academic and the industry. So they bring us the real data in stock price. So this is I don't say this anyway. So this is real data. And the point is that in finance area, we are interested in the correlation matrix of this time series. And because the correlation matrix will give you a lot of information. For instance, the correlation between the two stock prices and the companies. And the point is that we use this classical data we encode this classical data into quantum state to realize this quantum state. Here, the AJT is the JT element of the this table. And the good thing and the interesting thing is that by tracing out the time component of this approximated data vector, we arrive at this density matrix. So low stock is a density matrix. It's not a ket vector, it's a matrix living in the Hilbert space. And interestingly, this is exactly the correlation matrix of this stock price time series. So CJK is a correlation matrix. And of course, we shouldn't access to each component of the correlation matrix because this is huge. So we are especially interested in this quantity, which is called SVD entropy. That tells you the global trend of this stock price time series. And actually, so this orange one corresponds to this SVD entropy. And you can see actually that these four companies are not so strongly correlated in usual time, but at some point of time they are strongly correlated. Yeah, so this is global trend, right? And this point actually corresponds to the financial crash. I forgot the name of the Lehman shock. Yeah, actually, so this at a point Lehman shock occurs, and they are strongly correlated, and we can see actually this trend. Yes, I think this is a kind of interesting application because this calculation doesn't require the precise calculation. Just we are interested in the global trend about which point of time they are strongly correlated or not. So I think this kind of because this approximation, this encoding scheme only allows us to approximately realize the target quantum state in the quantum device. The next application is to the classifier. The GAN, the Generative Advisory Network, is often is an interesting framework in classical machine learning. So this scheme is usually used for training this point, the generator, and the classifier, discriminator. But in this framework, we replace this classical part with the quantum part. So this network is composed of the quantum generator and the classical discriminator, which also works as the classical classifier. So the goal is to so the goal of this discriminator is to distinguish the true data and the fake data. So the quantum device produces fake data that eventually approximate the true data. So if you train the whole entire network, then this guy is trained so that this discriminator or classifier tries to distinguish these two data, and this generator will generate the data that approximate the true data. Then finally, this discriminator, the classical classifier, will be enhanced by this device. The idea behind this scheme is that the quantum device could produce a probability distribution, which is hard to mimic by classical sampling. So this is called the quantum sampling supremacy, which was also have been deeply investigated, and there are a lot of theoretical results on this. So and actually, this scheme relies on such a theory, And we tested this scheme by numerical simulation. And this is the case of the quantum generator. This is the case of the corresponding the classical generator. So in this case, so both systems are classical one. And the quantum generator can be quite small, just 32 parameters contained. But the classical generator has to have over 3,000 parameters. And because this is kind of a deep neural network, we need to train this system a lot of times. Actually, the 1,000 learning steps is necessary to reach the accuracy over 70%. But in the quantum case, only the 100 learning steps is enough to achieve the similar performance. So that means the classical compared to the classical one, the quantum system can be small. And the concept of this is basically to train the classical system, which one? This one, by the quantum system. The goal is to train the classical one, not the quantum one. So we don't need the precise performance of the high level performance of the quantum device, just to train the classical one. So the mixed state with noise can be allowed in the quantum case. So I think this is a suitable application in this device, noisy devices. Okay, so finally, I wanted to show you kind of the fundamentals in classical, the quantum machine learning. I was inspired by this paper published 4 years ago, and actually this is a kind of the breakthrough in classical machine learning, especially the magic of the deep learning. So deep learning works quite well, but the mechanism why such a deep learning works well, it's quite mysterious and deep questions, and still a lot of argument occurred in this classical machine learning area. So the idea is it's quite simple. We want to minimize this cost function, whereas an XA is an input of data, the YA is a given training output. So we want to minimize this one, and take the usual gradient method to optimize, so minimize this cost function. And the function, so this paper looked at the function rather than the cost function. The function is an output of the neural network. And by the simple calculation, we arrive at this equation of f. So the f is changing in time, subjected to this equation, dynamic equation. And this part is called the neural tangent kernel, whereas an f is an output function, and the gradient, the product of the gradient appears in this part. And of course, this is in general the nonlinear function, which is a function in time. Here the time t appears in this LTK. So of course we cannot solve this equation. It's nonlinear and time-dependent, complicated function, so we cannot solve. But very interestingly, if you increase the number of the widths, this guy, infinitely large, then this part becomes time invariant. So this is just a constant matrix. Then you can see this is okay, this is just a linear equation. You can solve this equation, which is surprising, I think. And eventually, we have the explicit solution of this functional dynamics, and see that this output function actually exactly converges to the goal, the target, the YA, that's the training output function. Yeah, so actually this is, I think, the breakthrough and the NTK, the deep learning, and I wanted to apply this idea to the quantum case as well. So this is a summary. The NTK regime, randomly chosen initial parameters don't change. Yeah, so actually the parameter doesn't change as well. So we don't need to train the parameters a lot, just randomly chosen parameters, and around such initial parameters, that's a solution. So that's a very surprising result. Yeah. Yeah. Actually, there are some. Recently, we find some applications, extension of this idea to quantum regime. Yeah. The Antonio has a paper on this paper, the representation learning and neural tangent kernels. And the idea is similar to the classical case. We look at the cost function, and training dynamics and the functional dynamics is obtained as well. And so this part is called the quantum NTK, neural tangent kernel. And an idea is that the classical case, this guy, it becomes time invariant when you increase the number of the parameters or the widths. But this size, if I correctly understand, this is still the open problem. And they assume the frozen arithmetic regime, whereas MTK doesn't change. This is assumption. And then we can solve this equation analytically. And we arrive at the linear differential equation that is solvable. And this is solution. And actually, this assumption was verified in MEXT simulation, which is consistent with the theory. So I think this is a really interesting approach. And almost at the same time, we propose this approach related to the NTK, quantum NTK approach. So in our case, actually, so for this case, he didn't. He looked at only the purely classical quantum case, but our case, the entire system is composed of the classical and quantum. Quantum and classical, and the quantum part is not trained. We only focus on the training the classical part. Well, in this sense, I think this is not the usual quantum machine learning scheme. But later I'll show the remark that this has a kind of relevant reason why this scheme is important. So anyway, so this is a quantum state, a quantum system where X is input data encoded into the unitary operator. And we randomly choose the unitary operator and measure the measurement. Then, so this corresponds to the random measurement on the quantum system. And the measurement result is transferred to the classical neural network, which contains a tunable parameters. So we look at the entire the function is concatenation of the quantum and the classical function. So this is the cost, and as usual, we wanted to minimize this cost function using the gradient method. So this is the precise information about the measurement observable and random unitaries. Yeah, and in the classical case, we can arrive at this functional dynamics, and quantum NTK can be defined as well. And here's the theoretical result. If you increase the number of the widths in the classical part, this one, if you increase the widths infinitely large, then this quantum NTK becomes time invariant. So it's exactly the same as in the classical case. And especially if you take the cost function as a mean squared error, then the dynamics becomes the linear dynamical equation, which is solvable, and you arrive at the explicit formula of the final cost function, final function. And interestingly, this contains this actually is a kernel function, where this highlighted part corresponds to the kernel, and the y appears here. So this is exactly the kernel function, and the projection matrix appears in this part. That is a quantum effect. The rho xk is a reduced density matrix corresponding to the original quantum state appears in this part. So interestingly, the reduced density matrix appears in the kernel, and if you increase, this is just a case of the single the layered classical network. So if you increase the number of the layers, like a deep neural network, then the output function becomes a nonlinear function in terms of this reduced density matrix. So the expressibility becomes enhanced. So before showing the result, I would like to give it a remark that why such a form has a relevant. This is a relevant scheme, and I took this paper recently published. This is an idea called the classical shadow. So this is a quantum state you're interested in, but is unknown. So you do the random measurement on it and construct the reduced density, also the density matrix that approximate the original law. So of course, rho and sigma t are different. But so for many relevant situations like estimating the sum observable or the or fidelity, and then this sigma t, which is an approximation of law, works there as an approximator. So this sigma t law, which is called a snapshot of the quantum state, can be used for constructing the output function that for the purpose of the machine learning. Yeah, and so training set, and you construct the snapshot depending on the input, and you construct the output, the approximator, the predictor for the machine learning purpose. And actually, you can see this has a very similar schematic in our case, where we are interested in the quantum state, and you will do the random measurement on it, and construct the machine learning, classical machine learning neural network, followed by this part. So we have the interpretation that the proposed scheme is doing the same. I don't know but the machine learning scheme with this part, with this the idea. So in other words, we can skip the process of constructing the shadow or the snapshot, and directly construct the machine learning approximator corresponding to this quantum machine. Yeah, so this is the reason why I think that this has a relevant reason for as a quantum machine learning scheme. So finally, this one is an application of this schematic. And actually, in this setup, we are interested in the quantum data rather than classical data. The situation is that the input is a parameter specifying the system, like temperature or the interaction strength. So anyway, the x corresponds to the quantity that specify your system. Yeah, and then you can construct the quantum state depending on the xa. If you change the parameters, then of course this rho changes as well. And if you change the interaction strength, then the rho xa also changes. So yeah, and this is unknown. You don't know this quantum state. And later we do the measurement which can be unknown, because in general the measurement process is really complicated, and so it could be unknown. So anyway, so you have some information after the measurement result. For instance, this is the gx is a hidden function, and you arrive at this output quantity, which corresponds to, for instance, total magnetization of the matter, for instance. Yeah, actually, so this YA is an output, and this is XA is an input that we are given this training data. And the goal is to approximate. The goal is to construct an approximator with a predictor for the unseen quantity YA. And actually, for this case, this scheme I think has a clear quantum advantage over the classical case, because in our case, the low A, this unknown state could be regarded as an input. So this input is directly given to us, and we do the random measurement on it and construct the classical neural network and construct a predictor. And the full quantum model is also can do the same thing. But in this case, the quantum state, and after the quantum state is given to us, then we construct a quantum parameterized quantum circuit, and do the measurement at the end of the quantum circuit, and construct a predictor. But the full classical model, which is obviously weaker than these two guys, because XA is an input and Y is an output, and we cannot have access to the quantum state. So what we can do is just to construct a classical neural network given the training data. And the result is quite simple. This blue line corresponds. So this is an error. So the smaller is better. So this blue line corresponds to the hybrid quantum. Excuse me, case, and this blue, the green one is full quantum model, which becomes worse when you increase the number of the qubit. And the classical one is worse than these two guys for almost all cases. So this is an example where we can use this schematic for showing the quantum advantage. in this specific situation. All right, so this is a summary of my talk, and I have shown the overfitting and regularization. And the concept is that overfitting occurs in quantum case as well. Actually, this is a kind of a new finding, and the classical technique is can be used, effectively used, to resolve such an issue. Yeah, actually, there are a lot of works in classical machine learning, so we should use those ideas. And also, I have shown the two applications to finance and classification problems. The variational method could be used for realizing an approximate data encoding. And actually, data encoding is a key point in the quantum machine learning applications. And this requires us to shouldn't look at the problems that requires high precision. So the important thing is that what is a good problem for us? And in our case, we have calculated the SVD entropy for the time series of stock prices. And actually, for this problem, we don't need we are not interested in each component, but rather the global trend of the time series. And also in the GAN application, we use the quantum system to train the classical system. And finally, I have shown the kind of theoretical result, fundamentals in the quantum machine learning model. And the important fact is that we should use random measurement to extract the features of the quantum state. And the resultant result is that we can solve the dynamical equation of the function and can construct the kernel. So actually, the kernel is automatically constructed in the form that includes a reduced density matrix of the quantum state. Yeah, so this is summary. Thank you very much.
Thank you very much, Professor Yamamoto. Is there any question for Professor Yamamoto?
In the comparison you did between quantum and classical, what were you counting as, on the axis you had qubits, what were you counting for the classical and the classical plus quantum?
So you were talking about the last part?
Yes.
Okay, yeah, and my actually it's a vague and abstract way, but let's think about superconducting devices which are interested in to see the future. When you change the interaction of between the qubits, then some properties change as well. But we wanted to have a predictor for this dynamics. So first, such a quantum state is given to us. Then we do the quantum computation later, random measurement and the Clifford measurement and blah blah blah. And then, I mean, the preparation stage and the computation stage could be, operated in the smooth manner. We prepare the quantum state our interested, and later we do the computation on the same device. Does that make sense? Okay, yeah.
Any other questions?
Nice talk, thanks. Question about the last part. So we note that, right, so if we are in this over-parameterized regime, then the dynamics for the equations for the gradient descent, they decouple, and then we have this exponential decay. Yeah. Do you know of any other situations in which we can analytically predict something about those equations, like gradient dynamics equations?
So your question is that we finally arrive at the explicit analytic solution of the equation and what we can do with that predictor. Mm-hmm. Is that your question?
My question is that is there any other regime other than the over-parameterized one
okay. Any other regime
for which you have an analytical... I I don't have an answer to that.
I
I think the answer is no, but I'm asking you. Maybe you have a different.
Thank you. Good question. Actually, this is the analytic. If the dynamics is in the analytic regime, then the dynamics is frozen, and we can solve the equation. But it is still an open question. In what situation, the condition, the analytic regime appears? Yeah.
Right. Thanks.
We have time for one or more questions.
Thank you for interesting talk. So I have a question about the first part, so overfitting part.
Yeah.
So you applied a dropout for the quantum circuit, and I think if you replace a C node with a control RY gate, for example, so you can we can see this dropout as a kind of a parameterized quantum circuit, so same as other parameters. So yeah, I'm curious. So optimizing the control node part as well as the other parameterized circuit at the same time. What is?
Yeah, actually, we haven't tried the dropout for such a parameterized entangling gate, but that is an interesting question. And this is the same question that I got from the referee from the paper.
Yeah, so I think since there's been questions about the last part and questions about the first part, I think I have a question about the middle one. So I do have a question about the quantum generative adversarial network. I wonder what kind of data set structure you guys use for that benchmarking?
Yeah, actually, this data shown here, and this is a kind of we originally tested the MNIST data.
Okay.
But that didn't work well, so we changed the refined model, simplified the data set.
And can you point towards any direction where we may expect computational advantage in generative adversarial networks in particular data sets?
The computational advantage is still the missing part in this schematic, so that's a really important open question. Yeah.
Thank you. And maybe the last question: have you compared this data classification with a quantum kernel classifier?
Yeah, we didn't do that. So you were asking the performance of the pure quantum kernel classifier on this problem, but we didn't test it. Yeah.
Okay. Thank you.
Thanks.
Is there any other question? All right. If not, let's thank the speaker again.
Thank you.
So before closing and coming to an end, I want to invite Jake and Vera to the stage for some closing remarks. And yeah, thank again all the speakers. I think it's been a great conference on hybrid classical quantum computing. As you see, there's been a lot of topics that are cross-cutting in many different directions, from classical simulator of large-scale quantum systems, compiler, software stack, hybrid classical quantum computing workflows, and there's been a little bit of everything in these talks, and I want to thank all the speakers for sharing their thoughts and their technical expertise with everybody.